everyone, Mr. Lee here. In this video, we're going to do a part 2 to rotational inertia, but this time with a little bit of calculus. Let's begin. So the first thing I want to go over are the definitions of inertia and rotational inertia. Remember, Newton's first law of motion says an object in motion wants to stay in motion, and an object at rest wants to stay at rest. A lot of times that is called the law of inertia. So a object that wants to resist motion, or is more likely to resist motion, has a lot of inertia. Now, before we get into the rotating thing, just remember that we call it inertia mass when we're not talking about spinning objects. So the same comes true with rotational inertia, where instead of saying an object stays in motion, okay, we can say an object that is rotating will likely keep on rotating. A object that is not rotating will most likely not rotate as long as there is no outside torque or outside force. Okay, so this is a good place to start because that will actually help us set up for the rest of the notes. Now, in the previous video, we learned that rotational inertia has like just this basic equation called mr squared. Okay. Now, for all intents and purposes, this is what you need to know. However, we do need to know how you can find the rotational inertia when you're given a certain scenario. Now, let's do a quick little dive onto this equation before we continue. What this equation tells us is that the location of the mass, determines the rotational inertia. Okay, the location of the mass determines the rotational inertia, and that's where we get the R and the M. All right. So the first equation that you'll see on your equation sheet is this form of rotational inertia. The sum of the mass times the radius squared is equal to the rotational inertia. Now, the two equations look very similar, except this here we have a summation sign, or the sigma. Now, you use this equation. So this equation is on your equation sheet when we have different particles. Okay, and the particles are probably along the same axis. So let's do a quick example problem. So let's say we have a long rod. All right, so let's say we have a long rod, and on this long rod we are hanging two objects. We have object 1 here, and we have object 2 here. Okay, so let's say object 1 has a mass of 2 kilograms and object 2 has a mass of 4 kilograms, right? And we can say that the total length of the rod, so L total, is equal to 3 meters, right? So from end to end is 3 meters. Now, the cool thing about rotational inertia is all on how the object itself is rotating, okay? And I'll go over the different ways that we can see how this object is rotating. So let's say that we are going to rotate this object right in the middle of this rod. So what I'm going to do is I'm going to create a dotted line. I'm going to call this my axis of rotation. Okay. So what this means is that this rod will spin around, okay, in either direction. I just chose clockwise for the sake of the example. Where the pivot point will be right here in the circle, in the middle. So I'm going to put a giant X. That will be my pivot point. Okay, so it's going to rotate around that pivot point. Now, in order to determine the rotational inertia for this scenario, we can use the equation that we just came up with. I equals the sum of mr squared. So the very first thing I'm going to do is I'm going to write down the equation, and let's come up with the m and the r's. I'm going to call this object 1, or object 1, and we can call this object 2. So we can say m1 r1 squared plus m2 r2 squared. All right. Now, technically, the rod is also included here, and so I'm going to say that the rod, all right, it can be called m3 r3 squared. Now, I want to go a little bit more into that idea there, where I was talking about the technically part. All right. So the important idea is that we can use this equation to view particles, and so instead of viewing it as the system that you see before you, we can also imagine this. Instead of saying we have a 2 kilogram block, we can say there's a particle here called particle 1, and this particle 1 has a mass of 2. Okay. So instead of drawing out the entire rod, we can say that the rod is right here, right? The center of mass of the rod is right there, and we call that object 3, which is a rod. And instead of saying there's a 4 kilogram mass hanging from the far right side, we can say there's a particle right here, and we'll call this object 2. Okay, so we can view this as a system of just particles instead of what it actually is. And it's easier to view it in like something like this when we're doing our math. All right, so because we're rotating about this dotted line, the center of the rod, or the axis of rotation, we can come up with our different variables here. So we know that from the center to R1, okay, or mass 1, we can call that R1, and from the center to mass 2, we can call this R2. So if we were to put it in the calculator, we can say the mass of 1 is 2 times the radius. Now, I believe I said that the total length of the rod is 3, so R1 would be 1.5 squared. Okay, plus mass 2, which has a mass of 4 kilograms, also has 1.5 squared as the radius squared. And see what I do here? I don't think I gave you the mass of the rod. So let's just come up with the mass of the rod. We'll just say it's 1. Okay, so here we have 1, and the R3, because it's right at the origin, we can say the radius is 0, so 0 squared. Right, so if we were to do the math, we would get that all of this would be 13.5, and the units are kilograms per meter squared. 13.5 kilograms per meter squared, and that will be our I. All right, now what if we were to shift the axis of rotation, where instead of rotating throughout the middle, where we get a motion like this, okay, we choose one of the ends, and we rotate it around one of the ends, like so. Okay, so let's come up with a different scenario. Let's say we are going to be rotating it around the far left end. The far left end. So we have, let's create this rod here. Okay, and we can do, right, so we have object 2 there. We have object 4 here, the 4 kilogram, the 2 kilogram. All right, and we're rotating around the far left end. So right there. Okay. Now, in order to come up with the rotational inertia for this scenario, remember, I'm going to draw this again. We're going to view this like a system of particles, where we have a particle there, okay, which is mass 1, which is a 2 kilogram. We have a particle there, which is the rod itself, and we have a particle there, which is the 4 kilogram object. So 4 kilogram, 1 kilogram, and this is our 2 kilogram object. Okay, so we have 3 particles. Now, we're rotating this around the far left end, so the 2 kilogram. So scenario 1, we were rotating it throughout the middle, so something like this. Scenario 2, we're rotating it about the far end, so it's more of a hinge kind of action. All right, so in this case here, we would do the same. We would do mr squared, this is equal to I. All right, now remember, the entire length was 3, so let's start off with this one. So we get the 4 kilograms, 3 squared, plus from the middle, or from the far left to the middle, we have 1.5 squared. Okay, and if we plug that into the calculator, we should get a rotational inertia of 38.25 kilograms meters squared. All right, now it's important to know what this number means, so we're going to do a quick comparison. If I were to ask you which scenario will the system be easier to rotate, now remember, I is the rotational inertia, and is the quantity that tells us how likely it's going to resist that motion. So because, let's call this scenario A, we'll call this scenario B, we can say I of A is equal to 13.5, and we can say that I of B is equal to 38.25, right? If I were to ask you which one is easier to rotate, I would say that scenario 1, or scenario A, will be easier to rotate because it has less rotational inertia. And I would say that scenario B is harder to rotate because it has more rotational inertia. Right? Now, if I were to ask you this, so if we were to compare scenario B to, let's say, scenario C, where we have the same rod, except now we're going to be rotating it about the far right axis here, okay, where the 4 kilogram object is. All right, so we have that 4 kilogram object, we have this 2 kilogram object, like so. All right, so instead of rotating it around the leftward-most point, we're going to be rotating it around the rightward-most point there. Okay, So if we were to rotate it around there, remember, once again, we're rotating it as a system of particles. So we have particle 2 kilogram here, we have this 1 kilogram here, and then we have this 4 kilogram object here. Okay, but that's not going to actually have anything to do with the rotational inertia because it's at the origin. So if I were to come up with my formula, mr squared, it would be the 2 kilograms times the radius, which is 3 squared, plus the 1 kilogram object times 1.5 squared. And when we plug that into the calculator, we should get 20.25 kilograms meters squared. Okay, so that would be scenario C. So if I were to ask you, is it easier to rotate scenario C than to scenario B? You would say yes, because scenario C has a rotational inertia of 20.25, whereas scenario B has a rotational inertia of 38.25. Now, if we think about this in real life, this should kind of make sense, okay? Because in scenario B, we're trying to rotate an object that has a mass of 4 kilograms that's far out, right? Let's say you're pretending to hold it right around the 2 kilogram mark, and you're trying to rotate the stick that has a 4 kilogram object 3 meters away, compared to scenario C, where you're holding the object where the 4 kilogram location is, and you're trying to rotate this 2 kilogram object. Okay, and trying to rotate a 2 kilogram object is easier than trying to rotate a 4 kilogram object. Okay, so it should make sense that scenario B has a greater rotational inertia than scenario C. All right, so that's one form of the equation that you will find on your equation sheet. Here's another one. This one, we're going to get a little bit more into the calculus side of things. The equation looks like the following. All right. The rotational inertia. If you find the integral of r squared dm. All right, now let's dive into what this equation means. Well, actually, before we do that, you need to know that this equation is on your equation sheet. Okay, because we are going to go over one equation that is not on your equation sheet. This equation 1 is on your equation sheet, and this is for what we call extended bodies. Okay, and these extended bodies, you can think of like multiple particles all over the place, and they're not all neat in a row like we did before. Okay, or it doesn't have to be. Okay, so in order to fully go into this equation, let's try an example. All right, so let's come up with the same rod scenario. All right, so we have a rod here, and let's say that this rod has a length of r. So total length is we'll just say it's capital L. All right, and the total mass of this rod, we'll say it's capital M. So in order to understand the calculus behind this, right? Let's take a look at this dm. So what this dm tells us is that if you were to take a small little section of that rod, right? So if we were to cut out a small little section of this rod, okay, we can call that tiny little section dr, okay, because we took a tiny little slice. And with that tiny little slice, that tiny little slice will have a amount of mass. All right, I'm going to show you that with a different color. So that little slice has its own mass, and what we call that is dm. Okay, that tiny little part will be dm. So if we were to cut off a small chunk of that rod, dr, that chunk of the rod will have its own mass, and we call that dm. Right? So what you're trying to do is, with the help of calculus, you're doing this over an infinite amount of times in ever so slight or tiny little slices, and that's how we can come up with this integral. All right? So for this problem, let's see what we can do. Now, the first thing that I want to do is I'm going to create a little ratio. Okay, I want to know that for any length of rod called L, we have a certain amount of mass M. Okay, and from here we can say that we have dm over dl. Okay, a small section of mass from a small section of length rod L. Now, in order to match our variables up here in our equation, I'm going to change that L actually to dr. All right, there we go. Okay, now what's next? It's time to do some calculus. So if I take a look at the formula up above, Okay, I'm going to rewrite it over here. I is equal to the integral of r squared dm. I notice that this equation here has dm in it. Okay, and we just created a ratio with dm in it. So what I'm going to do is I'm going to rearrange this formula so that I have dm is equal to. Alright, so we have dm is equal to m divided by l times dr. Okay, I'm going to substitute that in. So I get I is equal to the integral of r squared from m divided by l dr. Now the reason why I want to do this is because I want to be able to actually integrate with this radius r, okay, because that's where my d is attached to. Okay, all right, now we want to set the boundaries for our integral. Now, I do find that a lot of students have difficulty with this, but as I said before, in order to set your boundaries, really think about what you're integrating from, okay, and that's where your d is attached to. So here we have dr. So that's going to be my physical constraint, right? What am I going from initial to final according to my my variable r? In order to answer that, let's take a look at our drawing. Okay, so if we take a look at our drawing here, let's set an axis of rotation here, right down the middle. Okay, so this is just like what we did in scenario 1, right? An axis of rotation right down the middle, where it's going to be rotating around like this. Okay, and we know that at the farthest left point here, I'll do this in blue, right? The farthest left point here to the farthest right point there, we can say that this farthest left point, if this is position 0, this would be negative 1/2 L. Okay, and this would be positive 1/2 L, right? Because this total rod length is L, right? And we're saying that this middle point will be position 0, the origin. So from there, we can set our boundaries for our integral. So our integral, we're going from the furthest left point, which is negative 1/2 L, to the furthest rightmost point, which is 1/2 L, r squared m divided by L dr. Next, what we need to do is we need to figure out, what are we actually integrating with? And at this point, you got to take out your constants. Okay, so I take a look at my integral there, and I can take out anything that is not associated with this dr, right? That variable r is what we are integrating. So I can take out here my m and my l, because my m, mass, and my l, my total length, is not my variable r, which is the distance away from the origin. So we have m over l, integral negative 1/2 L, 1/2 L, r squared, dr is my rotational inertia. All right, now at this point, I just got to integrate. So here we have m over l. Okay, if I integrate r squared, I get r cubed divided by 3, and then we have our boundaries there, 1/2 L, and then negative 1/2 L. All right. And what we got to do is we got to actually plug in our constraints into our r's. So we get m over l times 1/2 L cubed divided by 3 minus negative 1/2 L cubed. So that's all cubed right there, divided by 3. Okay. And with a little fancy algebra, we can figure this out. All right, so we get m over l. 1/2 cubed is what? 1/8. So we get 1/8 L cubed divided by 3. Negative 1/2 cubed will be negative 1/8 L cubed divided by 3. All right, and then here we have, what can we say? This is L cubed divided by 24 plus L cubed over 24. And then what we end up with is m over L is equal to 2L cubed divided by 24. And this turns out to just be ml cubed divided by 12L. And then we can simplify this even more by saying ml squared divided by 12. Wowie zowie. So you're able to get the rotational inertia for a rod. Now the cool thing is that there's actually a very handy chart that shows us all of this. So let's see how correct we were. So here, what you can do is you can just type into Google rotational inertia chart, and these are the common moments of inertia. So what we just found out is a rotational inertia through the center of a rod, and lo and behold, we found it, 1/12 ml squared. So what we're about to do is we're going to go from 1/12 ml squared to 1/3 ml squared, where when we shift the axis of rotation from the center to its outermost edge. Let's see how we can do this. Alright, now the first two formulas are found on your equation sheet. However, this third one is not. And this one is actually very, very important. You will see this, but it's not on your equation sheet. So this one is something that I would personally commit to memory. It is what we call the parallel axis theorem. Okay, so simply put, this is when the object is rotating at a distance away from the center of mass. Okay, so basically, if we have an object that should be rotating around its center of mass, so in a previous example, the rod was rotating around the middle of the rod. It's when we make this object rotate around any other point other than the center of mass, right? So what it would look like in drawing form is if we were to have a rod like so, and we say that the center of mass is right there in the middle, and we can say that the object will rotate around the center of mass like so, so something like this. Okay. Instead, what we do is we force this object to rotate. Let's choose the leftmost side. Okay, so the center of mass is still right there in the middle, but we are forcing this object to rotate around the leftmost part. So it's rotating around here. So instead of rotating like this, it's rotating like so. Okay. All right. Now, the formula for this, I guess that's a good place to start, where the parallel axis theorem formula is that your rotational inertia can be found by the rotational inertia, okay, about the center of mass, plus the mass times d squared. You know what? I'm going to use the lowercase d. I don't like the capitalized d. Okay, where let's define the variable, where I of the center of mass is just your average or your regular center of mass of the object. Okay, to see the rotational inertia for the object. Okay, m is the mass of the object. Okay, and d is the distance of the axis of rotation to the center of mass. So in our drawing here, it would be from here to here will be d. Okay, so let's try to get that rotational inertia. So we want to find the rotational inertia. I believe it was 1/3 ml squared. Okay, for this scenario here. All right, so this is what we know. We know that this length of this rod is length L. Okay, we know that we just found out the rotational center of mass, the rotational inertia, is 1/12 ml squared. And we said that the mass of this object is just m. All right, so these are our knowns. Oh, also d, the distance, is 1/2 of L. Okay, so with this being said, let's plug it into the equation that we just discovered up here. I is equal to I of the center of mass plus md squared. We said that the rotational inertia is 1/12 ml squared, plus the mass of the object is just m, and the distance from the axis of rotation to the center of mass, we said it was 1/2 of the L squared. All right, so at this point, all we gotta do is some algebra. 1/2 squared gives us 1/4 L squared. Okay, and what we can do here, 1/12 ml squared. I'm going to do like terms here. This will be 3/12 ml squared. 1/12 plus 3/12 gives us 4/12, and 4/12 is 1/3 ml squared. And lo and behold, we got to it. We got to the rotational inertia for a rod rotating about one of its ends. All right, let's do a quick little recap. We just covered 3 different formulas for rotational inertia. Okay, now we first started off with the idea that rotational inertia, for all intents and purposes, like if you're trying to solve something conceptually, I equals mr squared, a-okay, okay? But on your formula sheet, you will see this formula right there. I equals to the sum of mr squared, okay? And this is anything good for particles along an axis. We saw how the rotational inertia I, okay, can be changed based on what is rotating and how it's rotating, and we were able to determine, if that I has different values, what does it mean? Next, the second equation, which is on your equation sheet, okay, we saw how we can use a little bit of calculus to determine the rotational inertia. And last but not least, the equation that is not on your equation sheet, and so this is a very important one that you should memorize, is the parallel axis theorem. Okay, where I equals I of the center of mass plus md squared. All right, I'll see you next time. Bye-bye.